So how do we learn about atoms and molecules? We use what's called the scientific method. It's an approach to learning that is empirical, which means it's based on observation and experiment, rather than philosophical, where you just sit around and think about things. So the scientific method is just a process of investigation where we observe nature and its behavior, and we conduct tests, experiments, to see if those ideas are correct. The four key characteristics are the observation, the formulation of a hypothesis, experimentation, and then formulation of laws and theories. Now, the scientific method is not a rigid set of rules, do this, and this, and then you'll get a good result. It's just an approach to life. And I find myself using the scientific method to solve everyday life problems. I'm going to use this animated video to illustrate as I talk about the scientific method. There's really no sound with this, just a bunch of beeps and stuff. So we don't need to hear the background music. Animated science. So this is just like a wordless animation. So here we've got this guy. He's sitting here, the record's playing, he's reading books. He sees that one of these plants is very tall and the other plant is very short. And he's thinking, gosh, I wonder why they're not the same size. And so this is his observation. One of them is small and one of them is large. And so then you make a hypothesis, you try to figure out why. So here it's showing him measuring and writing that down. Those are observations. The hypothesis then comes as you try to figure out, well, why? Why is this one taller? Why is this one shorter? So one of his ideas is that reading to the plant makes it grow faster. The other is that the music made it grow faster. And the third idea was that the light made it grow faster. So how do you know which is right, if any? You do an experiment. So here he's enlisted some helpers, and they're each going to do an experiment to test these hypotheses. So the first one, he's got a control. He just measures this, and then he's going to compare that to a plant where he's reading to it. And he's going to do this over the course of a whole month. Science can be tedious. So he's reading to the book, comparing, making measurements again, and comparing this to a plant that he's not reading to. Very, very tedious. So here's person number 2. And this person is going to test the idea that it was the music playing that made the plant grow faster. So she's going to, I assume it's a she because she's got a pink bow in her hair. Does she have hair? I don't know. She's going to play music to a plant, and she's got another plant as a control group, and she's going to do this every day for a month and compare the growth of the plants. When we test experiments, we need to control variables, and that's why we've got that plant they're not doing anything to, because plants will grow by themselves. So here's the third test, that the third hypothesis, that the sunlight is causing the plant to grow faster. So this guy's got a plant without direct sunlight and another plant with sunlight, and he's comparing the height every day. Of course, we could have predicted what the results of this experiment are. So he's observing every day, making measurements. Some observations are quantitative, where they're measuring the physical height, others are qualitative. And so then they're going to look at the results of those experiments. It's a very old-fashioned computer. So reading did nothing, playing music did nothing, but the sunlight had a huge impact on the growth of that plant. So they took this observation, they developed some hypotheses, and did some tests and came up with a result. Any questions? So let's talk a little more detailed about the scientific method. So the first thing is the observation. Observation is also called data. Data sounds fancier, right? Observations or data is just a description of the matter, the behavior of nature. In that example, it was the height of the plant. We can use the mass, the temperature, the color, the texture. There's all different sorts of ways to observe things. An example from science, back in the 1700s, Antoine Lavoisier made very careful measurements of objects before and after burning them in closed containers. And he found that there was no change in the total mass of the material within the container during combustion. And this was surprising, because let's think about a fireplace, right? You take a piece of wood, big log, and you stick it in the fireplace, and you find that rare day when you're allowed to burn things, and you light the wood, and you have this nice crackling fire. And then later, when the wood is all burned up, do the ashes that are left in the fireplace weigh the same as the log that you put in there initially? No. Most of the mass is gone, right? The ashes are light and fluffy, and they're just very different than the wood. So this observation was not necessarily what was expected. So when you burn the wood, what happens to that matter? The mass, some of the mass is gone, it's much lighter. Where did the rest of it go? Well, the secret here is he was doing this in a closed container. When you burn wood, it actually combines carbon with oxygen and the hydrogen with oxygen, and you get carbon dioxide and water vapor, and that mostly goes up the chimney, and that's where most of the matter that was in the wood goes. But if it's in a closed container, then those gases can't escape. And Lavoisier observed that there was no change in mass. So the observations such as that lead to the formulation of a hypothesis. A hypothesis, it's a little better than a guess, but it's a tentative interpretation or a tentative explanation of those observations. Because just seeing what happens is nice, but we would really like to know why. We'd like to understand why that happens. So Lavoisier explained those observations by hypothesizing that when a substance burns, it combines with something that's in the air. A characteristic of a good hypothesis is that it's falsifiable. It needs to be something that you can test and potentially prove to be incorrect. In that little video example, two of the hypotheses turned out to be incorrect, right? One was that reading to the plant caused it to grow faster. The other was that playing music to the plant caused it to grow faster. Both of those were tested and found to be false. If you come up with an explanation that can't be tested, that doesn't do any good. Like, okay, well, Martians come in the middle of the night with little bicycle pumps and pump up I don't know. You could think of lots of strange things that couldn't be tested. That's not a good hypothesis. So the hypothesis has to be tested. These are done using experiments. Highly controlled procedures designed to generate observations. And it's not unusual for the actual experiment to be the very difficult part of the science, figuring out how to test the hypothesis, how to control for all the different variables. It's one of the things that makes understanding the effects of, say, your diet on your health very difficult, because there are so many variations among humans. You know, you feed oatmeal to a group of people and you measure their cholesterol. Well, are you also controlling how much alcohol they drink, how much exercise they get, what their genetics are? There's all these different things that you cannot control. Just one of the reasons why I like chemistry, because we're not dealing with living things, and so we can control them more frequently. So the results of the experiment may support that hypothesis, or they may prove it to be incorrect. And so if it proves to be incorrect, sometimes you discard the hypothesis. You say, well, that wasn't a good idea. And sometimes you just modify the hypothesis, and then you have to test it again. So after experimentation and confirmation of hypotheses, we have two results, scientific laws and scientific theories. And there's an important distinction between a law and a theory. A scientific law is a brief statement that summarizes past observations and predicts future ones. A law tells us what happens. It does not explain why. So from Lavoisier's experiments came the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. Doesn't explain how it happens, but it predicts that when you do a chemical reaction, provided that you confine it so you don't lose gases or something, you will end up with the same mass that you started with. Scientific laws can also be experimented upon. Scientists tend to be rather skeptical people. We're very curious, and it's just kind of fun to prove someone else wrong, right? So you've got this established scientific law, and you're like, well, I'm going to see if I can find a situation in which that is not true. And so you can test the law. Scientific laws are not things that you can choose not to obey, right? State law says, you have to obey the speed limit. The speed limit on Highway 99 down there is 70 miles an hour. You can choose to go faster than that, right? You can break the law. The law of gravity is a scientific law. You cannot choose to violate the law of gravity. You can't go up on the roof of this building and decide, I am not going to obey the law of gravity today, and just step off and go walking through the sky. It doesn't work. So scientific laws describe how nature behaves. Theories explain why. So when you have one or more well-established hypotheses, so these have been supported by experiment, those may be the basis, the starting point for a theory. And the theory is the model or the explanation for how nature is. It doesn't just say what it does, it also says why. So a little bit later, after Lavoisier, John Dalton came up with atomic theory. His atomic theory explained Lavoisier's law of conservation of mass. Atomic theory proposes that matter is composed of small indestructible particles called atoms. And since those particles are merely rearranging during a chemical reaction, the total amount of mass remains the same. So the idea here is, you can think of this in terms of Lego blocks. Say you have a Lego tree and a Lego car, and you could put them on a scale and weigh them, find out how much they weigh, and then you take those pieces apart and you put them together and make a tower out of them, using all the blocks. Is the mass of the tower going to be different than the mass of the car and the tree that you started with? No, because you're using the same blocks, right? In a chemical reaction, all that's happening is you're taking atoms and putting them together in different ways. Now, what can be a little mystifying about this is that some of the things are gases like carbon dioxide, and those can escape, and you might not notice that those went away. So we burn a log in the fireplace, and it seems like the mass has, gone down, and part of it's just gone. But is it actually gone? No. It is still around. It just went up the chimney. Right? And so the mass of the mass is conserved. It doesn't change. You can't create or destroy matter. Any questions? Theories are also validated by experiments. One thing that's a little disturbing is we can never prove anything to be correct. So we come up with a theory, like Dalton's atomic theory, and there's no way to prove that that's correct. We can try to prove it incorrect, and if we cannot prove something to be a theory to be incorrect, then we say, well, this is what we believe to be true. And then people are going to keep trying to disprove it. Now, Dalton's atomic theory, there were a couple of points there that were proven to be incorrect. Instead of just throwing out the whole theory, the theory's modified to take into account the new information. Okay, well, we need to change this piece and this piece. Theories are useful. They can help us predict what's going to happen if we do a similar thing in the future. And they can theories, because they explain, can help us predict what might happen in something that's not been observed before. So theories are as close to truth as you can get in science. So this is a flow chart representing the scientific method. It's not a linear process, it's a very circular process. And so typically you start with an observation that leads to a hypothesis. So like observing the plants that one was taller and one was shorter. And then you ask yourself why. You come up with a reason that you think is true, a hypothesis, and then you test it using an experiment. The experiment may confirm the hypothesis, or it may disprove the hypothesis, in which case you either throw it out or revise it. And then the new hypothesis gets tested by experiment, and you can spend an entire scientific career in that loop right there. Coming up with a hypothesis, testing it, changing it, etc. Observations can lead to laws. The observations such as when I hold out this pen and I let go of it, it falls to the floor. It does that every semester. It's called the law of gravity, right? And so observations can lead to a law, and then people test the law. Small children are kind of famous for testing the law of gravity. They can jump off of everything they can possibly fall off of, right? A well-established hypothesis can lead to a theory. Theories are also tested by experiment and confirmed or disproved. So lots of going around in circles there. So we should be able to identify whether a statement is a law or a theory. So which of these statements best explains the difference? So a law is truth, whereas a theory is a mere speculation. A law summarizes a series of related observations. A theory gives the underlying reasons for them. A theory describes what nature does. A law describes why nature does it. Which one do you think is true? C is very tempting. C is very tempting because that's very similar to what I said earlier, but it's exactly backwards. So the theory explains why, the law describes what. So C is not correct. The answer here is actually B. So the law summarizes observations like dropping a pen, law of gravity. Doesn't explain why, though. Scientists still do not completely understand what gravity is. We know how it works, but we don't know exactly why. Any questions?